Hello, chemists. Jolly here. Sorry, I know I sound terrible, but I sound a lot worse than I feel. Hence the reason we're really listening today to the frog. All right. Today we're going to be talking about organic bases. And so technically we're still in chapter 2, but we're just going to talk about the different types of elements that can actually act as the bases. And we're going to move into our new terminology, which is called nucleophiles. So let's go to our whiteboard. And so we are going to talk or get about organic bases. And just a little note, the term base is usually used when we're talking about acid-base chemistry. Or reactions. But after today, we will use the term nucleophile because that's more generic and that works for all reactions. So just a quick note here for terminology. Okay, there's our curly arrow notation. And we would end up with water with an extra proton plus Cl minus. And our terminology in the past is still the same. This is acid. This is the base. And remember, we're using Bronsted-Lowry. This is the conjugate acid. This is the conjugate base. So when we are using acid-base reactions, we use acid-base terminology and we would call it a base. But we could also call this the nucleophile because it is the attacker. And this one would be the electrophile because it's the one that was attacked. So again, the terms are okay. These are just generic for any reaction where base implies that you're dealing with protons. All right, let's go to our notes. Let me see, chapter 2. All right, so organic compounds as bases. So let's go back to what makes a good nucleophile. Anything with a lone pair or a pi bond, or even a polar bond, but the lone pairs and the pi bond are, of course, best. So any with an unpaired electron, okay? And also, we know that the pi bonds, but this is the acid-base chapter, so we're going to talk about those lone pairs first. All right. Well, what elements are out there that have lone pairs? Well, of course, we've got our nitrogen and our oxygen. And if you'll notice, the only one I listed for nitrogen was the amine. We'll talk about the amides later, but the best one is amine. These are actually called the organic bases. So carboxylic acids are known as the acids, while amines are called the organic bases because they really like to accept protons. Now, the oxygens, of course, there's tons of functional groups, the alcohols, the ethers, anything with a carbonyl, so the aldehydes, the ketones, the esters, the amides, and the carboxylic acids. This is talking about the carbonyl, not the nitrogen. All right, so let's talk about the nitrogen first. So we have our wonderful lone pair. It would act as the base. It would gain both a charge and an extra proton. And it would create the conjugate base. And so that is the generic form of an amine reacting. Okay, and the key here is, remember, nitrogen only likes 3 bonds. So if you give it that 4th one, it uses both of its lone pairs and it becomes positive. Well, alcohols will do pretty much the same thing. Now I'm not drawing equilibrium arrows. We'll worry about equilibrium later. And if you'll notice, it becomes also charged. And this group right here is called an alkyl because of the R group, oxonium because of the oxygen, and ion because the oxygen is charged. So that's just what you call a protonated alcohol. Ethers, no surprise, look pretty much the same way. And now we've got a protonated ether. And in this case, there are two alkyl groups. There's 1 and 2. So this is called a dialkyl. We have an oxygen that's positively charged, so oxonium ion. And then I don't have a fun name for carbonyls for you. But if we had a carbonyl, okay, don't care what it's attached to, so just put that, but I won't put any R groups. So again, we end up with a positively charged species, and then we have our conjugate base. All right, now this, let me change colors. This one has resonance, so I'm just going to put that here, but we will worry about that later. But you can protonate carbonyls, okay? All right, so that's talking about the lone pairs. Oh, look, there's our pi bonds, okay? Now, the alkenes and the alkynes are not the only thing with pi bonds. Carbonyls actually have them too, but generically, same thing, just like the lone pair, it's going to attack, a little plus there. The key here is, yes, you still end up with a positive and a negative, but this is a carbocation, okay? And we know carbocations are very reactive, and it's not just going to sit around. Normally what happens then is the chlorine or the conjugate base comes in. But anytime you break a pi bond, you are going to get that carbocation. And I just want to give you some possibilities. All right. So we've got alkenes, we've got alkynes, and we've got carbonyls. I just want to give you an example of each one. All right. I'm just going to write the HCl above the arrow. Remember, that just means reactant. All right, I'm going to attack. All right, there's two, whoops, sorry. There's two places that the carbocation could go. And we've talked about this in the past, but the most stable carbocation is the most substituted. Okay, that's called Markovnikov's rule. Markovnikov's rule is the most substituted carbocation is the most stable. And there's only two answers in organic chemistry, and that's sterics and electronics. And so this is an electronic question. So this would be a primary carbocation with only one attachment, and this would be a secondary carbocation with two attachments. And so this one wins. Okay, that's where the carbocation would go. So I'm going to put that wonderful carbocation in blue right there, and this hydrogen is the one that is on the terminal end. Now remember, this is a very, very reactive species, and so it goes on. Okay, that's not the point of this slide. So I'm not going to show you how we go on. We'll do that later. But the point is the carbocation is very reactive. All right, let's take a look at an alkene. Sorry, an alkyne. All right, we're going to break that pi bond. And again, we have a primary location and a secondary location. And so Markovnikov's rule says to put that carbocation right there. And so the hydrogen that I added goes right there, plus the Cl. And again, it will go on. But the first step, if you break a pi bond, you have to put two things in its place. And the first step is a carbocation, and then the thing that you added, in this case, that's a hydrogen. And then I'm going to draw the carbonyl a little funny. I'm going to draw it sideways, and I'll just make this one a ketone. Now remember, the lone pair can accept this hydrogen too, but I'm talking about the pi bond. Now, this isn't a Markovnikov issue. I'm asking who would rather have the positive charge, a carbon or an oxygen? And the oxygen is more electronegative. So if it's going to get anything, it's not a positive charge. So it will take the hydrogen, and the more electropositive element, carbon, will take the positive. And again, this is a carbocation, and it will go on. But that is an example of all of the pi bonds that we could see. And just a note here, let me change colors. Proton transfers, okay, are usually a first step in many, many reactions. So always keep your eye out for, an acidic proton, because it can usually get things started. All right, now I talked about the functional groups, just normal functional groups, but how could we make a really good base? Because in the nucleophile world, remember, negatives are better than lone pairs, which are better than pi bonds. So how could we make an even better base? Well, it would be awesome if we could make them negative. And if you want to make a good one, to create a strong base, begin with a weak acid. Because what is the little mantra? If you have a strong acid, it will make a weak conjugate base. If you have a weak acid, it will make a strong conjugate base. So if I want to make a really good base, I'm going to want to start with a weak acid. All right, now that probably doesn't mean a thing. So again, I'm going to jump over to the whiteboard. All right, strong acids. If I did that right, I muted myself and I didn't just cough in your ear. If I did, I apologize. All right, so strong acids are going to make weak conjugate bases. So for instance, let's take hydrochloric acid. Now, it's not just going to do this on its own, but the Lewis structure, or not the Lewis structure, the curly arrow would go to that plus Cl. All right, this is a strong acid, and this is the conjugate base. This is stable, which means it's happy. It's not reactive. Because the acid really wanted to come off, which means that was a really weak bond. And so the result gives you a conjugate base that is stable and not very reactive. Well, if we're trying to make bases, that's not what we want. All right, let's go for the best. Let's take an alkane. And remember, this won't just do it by itself, but let's say something came and attacked it. All right, this is a very weak acid, and this is a very strong conjugate base. In fact, this is the best base we can get. It has the strength of 50. It has the strength of 50. That is a very, very, very good base. Okay, so weak acids give very strong conjugate bases. All right. Now, is too strong even a thing for us? Well, the answer is yes. If you make the alkanide, okay, the one that I just made, it's going to attack everybody. So some of the ones that are more useful are called alk oxide. Okay, alk meaning there's an R group, ox meaning oxygen, and ide meaning negative charge. So your alk oxide ions are usually made from alcohols losing their protons. So ROH, somebody's going to come and rip off that hydrogen. And that is what you would be left with. This is a fairly weak acid, so this is a strong conjugate base. And then we can do specific ones. If this happened to be ethanol, ethanol would turn into ethoxide. And then, of course, a proton. T-butyl alcohol would turn into T-butoxide. And then, of course, the proton would go with somebody. So those are generally considered really good bases. They have pKa's somewhere between 16 and 18. Not so strong that it'll go attack everybody, but those are considered pretty good bases. The best solvent to go with those bases are their protonated form. So if you wanted ethoxide, you would just use this in ethanol. Or T-butoxide, its best solvent would be T-butanol, because then it could just rip its proton off and it would just make more of the base. All right, now the really strong one I was telling you about is the alkanide ion. And that is made by removing a halogen with a metal. Because remember, if that is the strongest, if it's the strongest base, it has to come from the weakest acid. And so it's very hard to remove that hydrogen. And so we're going to have to come up with a different way to remove it if we want to be able to use these alkanides. And we're going to do that by using lithium metal. Okay, so we're going to remove a halogen with a metal. All right, and so what you would do here is instead of just starting with an alkanide or an alkane, I'm going to start with an alkyl halide, and I'm going to react it with like lithium metal. Okay, not lithium ion, lithium metal. And then usually, of course, our best solvents are in an ether. And I'm not going to do the curly arrow notation, but if you'll trust me for now, we are going to make that bond. Okay. And then, of course, the halogen will be there. This is the alkanide. It's the alkanide. And technically, it's just a carbon connected to an alkane. So it has a pKa of 50. Very, very strong. Last but not least, I want to point out that we know something about the alkynes. So if it is a terminal alkyne, remember this has a pKa of 25. Okay, that's not horrible. It's not horrible. And so anything that's stronger than it will rip it off. So anybody with a pKa I apologize again. I've been talking a while and, well, my voice is going away. All right. So if we have a terminal alkyne, somebody with a pKa greater than or equal to 25 will come and rip it off. And we're going to make the alkynide ion. And I love this one. Okay, so this is the alkynide ion because it's not sterically hindered. The alkyne, remember, is linear, and so it can really get into places that other bases or other nucleophiles can't fit. All right, so recap. Don't forget, we have our nitrogens, we have our oxygens, and then, of course, our carbons. And we can either have the neutral, like up here, just lone pairs, or we could make them better bases by making them negatively charged, and the oxygen minus and the carbon minus are really pretty good strong bases. My one last thing, beware, beware, beware. If you are doing acid-base chemistry, always watch out for the solvent, because in water, okay, the strongest base possible is OH. And so the proton will go to anybody stronger, leaving just the OH. It's called the leveling effect. And we talked about this before, but let's just say, let's start with the alkynide. Let's say we started with the alkynide ion and we wanted it to attack, oh, I don't know. Who do I want it to attack? We'll just do a generic alcohol. And we'll say this one, so this has a pKa of 25. We'll say this one has a pKa of 18. And we're going to do this reaction in water. The problem is water has a pKa of 16. And so the base will always go after the weaker one. So it will react and give me this as the product instead of attacking this one. Which is what I was expecting as the product. So that's called the leveling effect. So when choosing your solvent, always beware. Polarity, okay, that's so that things come together and you're dissolving. But always watch that reactivity, because a weaker acid, okay, will always react. Okay, so this one would always go after the pKa of a 16 rather than a higher one. Or even if it was a 2080, you're still making product that you did not expect. And that's just called the leveling agent. Okay, that does it for acids and bases. So that was just a tie together of now looking at the base side of things. And the next chapter will be generic reactions and then alkyl halides. So until next time, jolly out.